Resistivity and resistance. How could the wire in the circuit affect the current? Let's go back to our water analogy. If wire is like a pipe and current is like water that flows through the pipe, if we had pipes with water in it, like over here, what could we do to the pipes to change the speed of the water? The analogy there is the current, the electrical current. We could change the cross-sectional area of the pipe. In the cross-sectional area, if you look at a pipe end on, and in here this is where the water is flowing, that we call the cross-sectional area. And if you knew the diameter of the pipe, you could cut that in half to get the radius, and then the cross-sectional area would be pi r squared. So if we make this bigger, more water is going to flow. Also, if we make the pipe longer, it will take longer for the water or the charges to get through. So if we go back to the electrical circuit, same amount of charge takes you a longer amount of time to get there, the current is decreasing. Every conductor conducts electric charge to a greater or lesser extent. The example that we had with the water pipe, we're going to apply to copper wire. When we increased the length of the pipe, we found out that we didn't conduct as much water. It took longer. So you would imagine that if you decrease the length, you would conduct more water. And that's what we're using here, this word conductivity. When we increase the cross-sectional area of the water pipe, more water flowed. So if we apply that to a wire, more charges would flow. So by decreasing the length of a wire or increasing the cross-sectional area, we will increase the conductivity of the wire. We're actually not going to use conductivity. We'll use something called resistivity, which is the inverse of conductivity. So if conductivity goes up, resistivity goes down. Each material, depending on what it's made of, will have a different resistivity. You might imagine that copper would have a very low resistivity, as that's what we use in wires, and glass would have a high resistivity. Current doesn't flow well in glass. We will abbreviate resistivity with the Greek letter rho right here. Very similar to a P. P is kind of like this. A rho is a little more curvy, okay? And you use that for resistivity. We now combine everything we learned. Resistance of a conductor is resistivity, the greater the resistivity, the greater resistance, times length of the conductor, greater length, more resistance, divided by or inversely proportional to the cross-sectional area. The bigger the cross-sectional area, the smaller the resistance. Resistance is measured in ohms, named after a German physicist. Ohm is the Greek letter omega, like this. Kind of write it like that. Cross-sectional area, A, measured in meters squared, like all areas. Length, L, is measured in meters. Then resistivity, rho, is measured in ohm meters. There's no special unit for it, it's just ohms times meters. Materials with a low resistivity. When you want to choose the material for your wire, you want to choose a material with low resistivity, because you'll be able to get more current flowing through it. What is the resistance of a good conductor? Well, on the previous page we talked about how we wanted to use materials with a low resistivity. And that is so we have a low resistance in the conducting wire. So the answer, we want a low resistance because more electric charges are free to move in a conductor. But in addition to resistivity, the length and the cross-sectional area also come into play. The length, you need whatever length is required to connect up your circuits. So you can't control that too much. However, the area, you can use different size wires. If you need more current to flow, you need a bigger, fatter wire, one with greater cross-sectional area. For lower currents, you would use a thinner wire. And once again, please click over here for a University of Colorado simulation about resistance. Here are some resistivities of common conductors. Remember, a conductor conducts electricity. Some conduct it very well, some not so well. Materials with a lower resistivity are better conductors. So you can see right here copper, which is what we use for household wiring, has a very low resistivity. 1.68 times 10 to the minus 8th ohm meters. Well, you might say, why don't we use silver for household wiring? Well, one reason certainly is the cost. Copper is a lot cheaper. And the other is you start getting into engineering properties. Copper is a stronger metal to use in houses. It doesn't rust, it doesn't tarnish, much better material. Gold is very good, and they'll actually use that in old printed circuit boards to make connections. And you can go all the way up here to nichrome, which would be 100 times 10 to the minus 8th ohm meters.